Okay, so just to recap Tuesday's lecture, I'll pose a problem to you and see what you say. So you know there is a big issue in audio systems about distortion. So especially the speakers. When you buy an expensive audio system, it's easy to make an amplifier today, which is good, but it's hard to make perfect speakers. So the question, why isn't it fixed with feedback? So for example, if you have an audio system, say you have two speakers, you are sitting here, so they're driven by an amplifier. Instead of trying to make perfect speakers, why don't you put a microphone here where you are sitting, or two microphones, feedback the signal, just like a feedback system, compare it to the input. That's the audio input. And any kind of distortion will be corrected just like an op-amp corrects the distortion. I see somebody already has an answer. Yeah?
What with the speakers, would they interfere with each other?
Okay, let's make it simple. There's ways around it, but let's make it simple with one speaker. The comment was maybe the speakers will interfere with each other. Okay, so we have only one speaker, like in a car in front of you, and instead of struggling to correct the distortion, making a perfect speaker, we pick up the sound where the listener is and close the loop to force the sound to be a perfect replica of the input. The same way as we close the loop in many other systems. Yes, please.
If your environment's not anechoic, then the room you're sitting in affects.
But this will fix it. You see, that's the beauty of feedback. Let's say there is some other disturbances. It will force the amplifier, if it's anechoic and you get some reflections, some noise, it will be like noise-canceling headphones. Anything it picks up which doesn't agree with the input, the amplifier will make an antiphase component to cancel it out, exactly like noise-canceling headphones work. So what's being done today? What's being done today, there is some feed-forward techniques. You're probably familiar with equalizers. There are boxes today which go in front of the amplifier, and they have all kinds of adjustments to compensate for the room. Not just treble and bass, but there is even systems which are more sophisticated. You do some tests on the room and you make some adjustments here to compensate for the room acoustics. So this is in a way feed forward. You know what the problem is. You feed forward a distorted signal to, for example, if the room attenuates high frequencies too much, you boost the high frequencies so it'll come out correct. So basically all audio systems today have no feedback, acoustic feedback, or feed forward with all kinds of buttons, equalizers. But why don't you simply close the loop and make it perfect? Yes?
Does that mean we don't have to carry a microphone from us?
No, because let's say that's your living room, the microphone can be installed in the couch. So that's your favorite couch, the microphone can be installed on the couch. Each time you sit down on the couch, it will be perfect sound. Yes?
Because sound travels much slower than
Ah! Somebody was paying attention Tuesday. Okay, what is a killer in feedback systems? Delay. Okay, so let's have a look at it a little bit. What is the delay, roughly, from your amplifier? Say, if you use an amplifier, this is a listener. What is the delay typically between the amplifier and the listener? In milliseconds, just an idea. So what is it? Typically, say if this is an amplifier, you are the listener, you are 3 meters away, what would delay be? A microsecond, a millisecond? Pardon? Okay, how much does 10 milliseconds is the right answer, because sound travels 300 meters a second. So 3 meters, it's a hundredth of a second, 10 milliseconds. Okay, so this delay is about 10 milliseconds. Now, if the delay is 10 milliseconds, what is the highest bandwidth you can achieve if you close the loop? So again, back to Tuesday, what does the delay do in a feedback system?
Changes phase.
Changes phase. And when does it become bad, really bad? Okay, so basically we know that if 10 milliseconds will become 180 degrees, it will be very bad. No feedback will work. Before that will also be bad, but for sure when 10 milliseconds becomes 180 degrees phase shift, nothing will work. So what frequency corresponds to that? Just elementary school math. How much? Just simple math. Okay. Okay, so if 180 degrees is 10 milliseconds, how much is a full wave? Come on guys, I know it's early, but wake up. If 180 degrees is 10 milliseconds, how much is 360 degrees, like a full sine wave? 20 milliseconds, right? Well, that's half a wave. 180 is half a wave, that's 10 milliseconds, so the whole wave is 20 milliseconds. So if the whole wave is 20 milliseconds, what is the frequency? Good. Okay. So, sure, because if this is t, the frequency is 1 over t, right? This is the length of time, 20 milliseconds. So in 1 second, there will be 50 of those cycles. So if you close the loop, that whole servo will stop working at below 50 hertz. Now, that's very bad because audio only starts at 20 hertz and goes to 20 kilohertz. But at 50 hertz, it will already not work. Okay? That's the reason why you can't use feedback in audio systems. Clear to everybody? Good. And you can actually see the effect of this as positive feedback. When you bring a mic to the amplifier, it starts holding because you get positive feedback, right? Typically holds at 100 hertz or a few hundred hertz because there is enough. Because if you bring the mic to the amplifier, you get feedback. The signal from the amplifier goes into the mic. But it doesn't take much of a frequency to make this feedback positive instead of negative because of this. So as soon as you bring the mic to the amplifier, to the speaker, it starts holding because there will be at least one frequency where the delay is 180 degrees, and the frequency doesn't have to be very high because we know that at 3 meters it will be 50 hertz, so even at 0.3 meters it will be 500 hertz, it's still within the range the system can oscillate. Okay? Good. So you always, when you think of servo, when you think of control, you always think of these numbers. The first killer is delay. And what is the second killer of servo systems? Good, resonance. How come only you said it? What about the rest? We just went over it Tuesday. So the second killer is resonance, and why is that?
Because
you get big phase changes. Okay, I didn't talk about the third killer of stability in servo systems because it's a bit outside the scope of this course, but the third killer is backlash. Okay, so if you have to steer a car which has a lot of play in the steering wheel, okay? So you're trying to follow a curved road, but you turn the steering wheel, the car doesn't turn because there's backlash. So you turn it a bit more, suddenly the car turns too much. And then you correct, you turn back, nothing happens because of backlash, you turn a lot more, the car oversteers. Okay, so the car goes unstable. So backlash also destabilizes servo systems. So these are the three big things, like delay is number 1, resonance number 2, and backlash, already kind of strange things, hysteresis, nonlinearities, backlash, some strange nonlinear effects. Let's lump it together and say highly nonlinear effect, especially backlash. This is a killer of any servo system. You can't stabilize it, but the backlash you can stabilize with advanced control, or what's called modern control theory, because you can predict it. Each time you reverse direction, you can add a certain amount of motion. Because this is a known thing if the backlash is constant. So the computer can know if he's going to reverse direction, throw in amount of backlash to compensate for it. And this gets into the realm of nonlinear servo or modern servo theory. And this is doable. For example, all machine tools do it, because machine tools have backlash, because lead screw, bearings. So when a machine tool changes direction, there is a backlash compensator in the software and throws in the extra motion of the motor. Okay? So remember that. So the three things always to worry about is number one, delay, number two, resonance, and number three, backlash. And if you don't find a solution for that, system will not work. And the backlash, there are solutions, some learning and some clever solutions. The delay, there is no solution. Okay, good. So this summarizes Tuesday's lecture, then we move into today's topic. So we are starting today's topic is what makes a good sensor. Remember, the course has three sections: sensors, interfaces, and actuators. Okay? So we're starting with what makes a good sensor. So in order to get you in the mood, what makes a good sensor, let's start with very early sensors, which were used for hundreds of years, nothing to do with electronics, but the principles are the same. So in general, what makes a very good sensor is a sensor which is very sensitive to the measured property, but is insensitive, doesn't respond at all to all other changes, environmental or other changes. So for example, if you want to measure weight, you want some kind of a sensor which is only sensitive to weight, but is not sensitive to temperature, it's not sensitive to vibration, not sensitive to air pressure. It just gets a big signal from the measured quality and is immune to any other changes. Okay, so in general that makes a good sensor. But even that is not always good enough, because there could be, it's sometimes hard to find such a solution which really doesn't react to anything except the measured quality. So let's take an example. If you wanted to measure volume, like all the things people measured is weight, volume, and distance. This was, even the Egyptians measured those. Okay? So let's think, for example, of an example. You want to measure volume. So even the Egyptians and the Greeks, they have a cup, and the cup had graduations. Okay, you put in a liquid, and you could measure volume by this cup, or typically it had a mark. A mark, it was 1 unit of volume, and you could pour a liquid, that is a volume. But if the temperature changes, two things happen. Okay? The liquid itself expands, and the cup expands. So although you want something which only responds to volume, immediately you get mixed in some other variable, temperature. Okay? So let's say you don't care about the liquid expanding, because let's say it's okay, I am measuring the volume at this temperature. Okay? But the cup is made from a different material as the liquid, so how do you get around the cup expanding? So of course so you think about it, you say, well, I can put a thermometer here, old-fashioned thermometer attached to the cup, and I can have a correction table. This was possible 1,000 years ago, right? You measure the volume, you look up at the temperature, and you enter some correction for the cup changing size. Okay, so here we are getting the kind of the first idea is compensation, some kind of measure, some correction or compensation. And this is done in a lot of sensors today. I mean, the temperature is measured with a thermocouple, you know, everything is more sophisticated, but the principle, if you have variables you can't get rid of, you measure the disturbance and correct for it. For example, all systems today which measure lengths accurately have a thermometer and they correct for temperature, because the thing you measure changes with temperature. Okay, but let's say you want to make something even more accurate, because let's say you get worried that maybe the cup not only changes with temperature, maybe it changes with air pressure, maybe it changes with age, maybe there's other factors, and you want a very accurate measurement. So can somebody think of a way to measure volume with a cup, and even if you don't know the properties of the cup, which will be corrected for all changes? Yes.
Put the cup and control them down.
Yes, but that is almost the same as this, measure the environment and correct. But it's true, but you don't even know what to control in this environment, right? Maybe you have to control the air pressure too, okay? Yeah, so obviously if you can control the environment, that works. But let's say if you can't control the environment, I think there was some idea there.
I was going to say you could have a standard bit of water.
Ah, now you're getting somewhere. And how does a standard bit of water look?
And you can have one bucket somewhere that you pour into whatever jar or beaker you're using at the time. Kind of thing.
Yes, okay. So basically, you are almost there, because there is another way of measuring something, is comparing to a reference. But you have to design it that the reference is as identical as possible to this, so all the changes will affect both. Okay? So let's say you very carefully measure a liter of water and put it in another cup like this, but this cup is sealed. So this one is a reference, has water. This is a reference. You close it up, and even in the old days they could do that. Put a cap on it and seal it. Okay? I mean, people knew even South years ago how to make a sealed glass vessel. If not, you seal it with some tar. Now, this is your reference. You make a mark. You have a little scale here. Now, if temperature will expand the vessels, both will expand the same way. So you're doing a ratio measurement. Okay? Say a liter used to say 1, and this was whatever it says. Now because this expanded, this now says 0.9. You say, no problem, I'll take whatever that reads, divide by 0.9. Is that clear to everybody? Let's say because of temperature, the container, which is made of metal, increased, and so let's say it reads now a bit less, so this gives you the correction factor, but this correction factor takes into account everything, even the things you don't know. Because if air pressure affected it, if temperature affected it, if aging affected it, these two containers are identical. So if the containers change with age, most likely they change the same. So even the effects you can't think about will be taken care of. Why do you have to seal this one?
Make sure that the water goes up.
Of course, otherwise the water evaporates, has to be sealed, yeah.
But, if the temperature rises,
Yeah.
the pressure of the gas inside will rise and then will be.
Ah, excellent point.
So maybe
The answer is if you put in the numbers, you see it doesn't matter because the water is hardly compressible. So this is only a correction. This will change, say, from 1 to 1.1, let's say, 1.01. Okay? Now, air is like 1,000,000 times more compressible than water. So the error, because the air pressure goes up by 1 part in 1,000, is completely negligible. But the thought is correct. You have to calculate that to say it doesn't matter, the air pressure doesn't matter. Now there is another solution to that. If you're really worried, you seal it off with a piece of rubber or something. So if the pressure rises, this will just bulge. But it turns out if you calculate, you don't need to do that. Because think of it, if the pressure rises, if the pressure doubles from atmospheric to double, okay, the volume of the air will be half, just because of its gas law, okay? So doubling the pressure, half the volume of every gas. Now, if you double the pressure on water, the shrinking of the water will be imperceptible. And the expansion of the container, if it's metal, will be hardly perceptible. So the truth is, because this changes so little, it's just a correction, you can ignore the air pressure. But if you're worried about, seal it with a thin metal membrane like a jar of jam. So this thin membrane can bulge out. Good. Okay, so now I'll give you one more example just to get you in the mind frame of thinking about sensors. Let's say we're talking not about volume, but we're talking about weight. So you can measure weight in two ways, with a balance, okay? You can have a balance, and this is an unknown weight you're trying to measure, and you put some known weights here, and you balance it, okay? Okay? Or you can measure weight by, say, hanging it, the weight from a spring. Let's say you have a cantilever or a spring, and you hang the unknown weight, and you have a pointer here, and you have a scale, just like a fish scale. Okay? Now, theoretically, which is a more accurate way to measure? Pardon?
The balance.
Why?
Because you always know that the weights that you're comparing are the same. Like you have a known weight that you
But you can calibrate the spring. You can put these weights on the spring and calibrate the spring with the same
Yeah,
weights.
but they won't change. I guess the spring constant will change with.
Okay, so first, yes, the spring constant can change, although typically a good spring doesn't, but you're right. It's a bit safer because you're comparing a weight to a weight, you don't rely on the spring. Okay? Now, there is a bigger factor than that. Let's say the spring constant, a good spring will only change 1 part in 1,000 or less. But there's a bigger factor here which causes an error here and doesn't cause an error here. Pardon? Again, a spring is very linear. A good spring is linear to 0.01%. Yes?
Temperature can expand or shrink the spring?
Pardon?
Temperature can expand or shrink the spring?
Yes, temperature will affect the spring, and more so, temperature can affect the spring constant. Because you're not so sensitive to the length of the spring here, you are sensitive to the change in spring constant, because it also changes temperature. So yes, the answer is correct. Still, this isn't the biggest factor still, yes?
Has to depend on the accuracy of your scale that you're using a little bit? Is this like a bias?
Yes, okay, so that you brought up a very good point, and I'll get to it because that's my next topic. This sensor is what's called a null sensor. All what you're trying to do, you don't have a meter here, you just need a null detector. You're trying to null it out by comparing two things. And I'll talk about it next, because null sensors are always more accurate than full range sensors. But there's still one factor nobody mentioned. Yes? Gravity. And why is that a bigger factor? Because I said the linearity of the spring, the change of the spring constant with temperature, they are usually in the ppm level. Right? But gravity is a bigger factor.
Depending on altitude, maybe?
Yeah, because gravity depends on altitude. So say if I go between sea level and Whistler, how much will the measurement change in a thing like this, roughly? So make a quick estimate. So how high is Whistler? I don't know myself, but I can how high is Whistler in feet? Who is a skier here? How high is Whistler? Let's say a kilometer. I don't know. I'm guessing. Okay. So let's say you go from sea level, which we are here, to Whistler, 1 kilometer difference. How much does gravity change over 1 kilometer? So just a rough estimate. Does it change 1%, 10%? So there is a formula for gravity, right? So there is a formula, there's two masses, they attract each other, so there is an earth and a small mass, and just for primitive simulation, we can say, let's say all the mass of the earth is concentrated here. What is the distance between the center of the earth and where we are now? Very roughly.
6,000?
Yeah, 6,000 kilometers, very good. 6,000 kilometers. Very roughly, and we change 1 kilometer, so we change 1 part in 6,000, okay? So how much will the reading change if we change the distance 1 part in 6,000?
Force will be proportional to the distance squared.
Ah,
So if you change 1 kilometer, then
okay, so if the change is 1 part is 6,000, but the result is proportional to the change squared. So how much will the change squared be? Pardon?
1 over the distance squared.
But how much is it? That roughly? Again, that's high school math, you know. If something changes 1% and the result is proportional to the change squared, so if the variable changes 1%, how much will the result change? Guys, what's going on? It's a very simple high school question. You have a y equals x squared. X changes 1%. How many percent does y change?
0.1.
Very good. And how did you arrive at that?
Just multiplying. When you square it, you go one back.
Listen, guys, you have to learn to do things in your head very fast. And I want to explain to you why. Because your generation always says we look it up. You know, you can't, and it's a serious problem because you can't invent anything if you have to look things up. And the reason is that, as some American inventor said, that to invent is to combine two known things. But if you don't know anything, there's nothing to combine. It's a big problem, okay? So if you want to invent, you have to have all the facts floating in your head simultaneously. And then your brain combines things. But if you have to look up A and look up B, you'll never have A and B floating in your head simultaneously, so you wouldn't be able to invent. I'm dead serious. So since you all want to be successful in technology and make a lot of money and so on, you will have to come up with new ideas. Okay, and for that, you have to have things floating in your head at the same time. Okay, and you have to very quickly estimate in your head in milliseconds, how big is this, how big is that, is it important, is it not important? Because if you do it sequentially, if everything you have to look up, as I said, you'll never be able to invent. So you have to get used to the habit to quickly think about things and not Google them. And the other problem is there is a lot of things you don't even know exist, so you can't Google them because you don't know what they're called. And I think we'll run, in this course, you'll run into a lot of concepts that you never heard the name of the concept. So you'll never be able to Google it because you didn't even know such a concept exists. Okay, like tellurimeter, which we'll talk about later and so on. So you have to get into the habit of thinking and doing things in your head. So in order to estimate squares and cubes of numbers which are close to 1, you always use what's called the binomial expansion. So you know that if you have 1 plus a to the power of n, this equals to 1 plus na, and then there are more terms which have n squared. But a is much smaller than 1 because we're talking like 1%, so it's 1 plus 0.01. So all the higher order terms which have here the next term will have a squared, and then we'll have a cube. All these terms you can ignore. Okay, so the approximation of 1 plus a to the power of n is 1 plus na. So if you have 1%, you have 1 plus 0.01, 1 plus 0.01 squared, it is simply 1 plus 2 times this, 0.02. Okay? So 1% error, if you square it, gives you 2%. Okay? So this thing is something you have to have in your head so you don't run to a calculator if you have a cube order system, third order system, the error in x is 1%, the error in the system is 3%. Right? Because a is 0.01 and n is 3, so it's 1 plus 3a. And all the other terms you can ignore because 1% squared is already 10 to minus 4. Forget about it. So please keep that in mind because this kind of speeds up your thinking a lot about errors and things like that. Okay? That's a binomial expansion, right? It's like Newton's binomial. Okay. So we have 1 over 6,000 squared, so the error will be 1 in 3,000, right? Because the way I write it is actually 1 plus 1 over 6,000, and I square that, so this becomes 2 over 6,000. Now 1 in 3,000 is 0.3%. So basically, just the change in gravity going from here to Whistler will give me a 0.3% error, okay, which is big. It's a much bigger error than the spring changing and so on. Okay? So back to the question, so what do I do? So this is good because gravity affects both sides equally. So if I go to Whistler, this gets lighter, but the reference gets lighter. So the scale is correct. Okay? But this thing will depend on many things, temperature, blah, 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 plus altitude. And there are places higher than Whistler, so the error will go up even higher, like the square. So how can I fix that it will not depend on gravity? So the first idea must be something similar to this idea, using some reference, right? So how do I do that?
Have a spring with a known weight.
Yeah, that's the gentleman answer, yes?
Yeah, I was going to say the same.
So have what?
Have a known mass.
Known mass and spring. Okay, so one way to correct it is have a calibrator, okay? And actually there's an elegant way of doing it, that instead of this pointing at a scale, this can be pointing at a scale which is hanging from a calibrator with a weight. Okay? So if gravity goes up, this thing will stretch more, but the scale will stretch by the same amount. Right? So you don't even have to do the calculation. Here you had to do the calculation to correct it. Here you can just hang the scale on a same spring in a known mass, so the scale will automatically move to correct the reading. Is that clear?
The mass that you're trying to measure
Yes.
and the mass of the scale
Yeah.
plus the known mass.
Yeah.
If they don't match and the gravity goes up, won't be the displacement will be like different?
No, it turns out it doesn't matter, because it turns out, if you think it through, it doesn't matter, because it's a scale factor. So let's say, if you do it right, you can make it compensate because it's a scale factor. Well, yeah, what you need to do is a stretchable scale, actually. To fully correct, you really need a stretchable scale, not a fixed scale. You're right, but you can do that too. There is ways to do it that will fully correct. Right now it's only correct around the 1 point, around the 0 with the same mass. So that's a good point, but even that can be corrected. Imagine the scale is made of rubber, okay, and you hang a weight. And this rubber is a spring, or the scale is a spring. So the scale stretches and you can read it to any weight. But what matters is the principle. The matter is you have a reference and you do that. Now, can somebody think of a way that you can... So we talked about this is good because it's a null sensor. This and this are correction by having a reference, which is also a very common mode. Okay? And there is even a more elegant way to fix that problem. And let's see if somebody can think of it. I want to measure that mass without having to correct for gravity. Let's say I want to go in a spaceship, gravity can go to 0, but I still want to measure the mass of object in a spaceship, in space station. Very nice. What I can do, I can just pluck it and it will oscillate. And it will oscillate at a frequency 1 over 2, right where I have more space, it will oscillate at a frequency of 1 over 2 pi square root of k over m, where k is a spring constant, m is a mass. And this will be totally gravity independent. Okay, so that's a nice example that there is a good solution and a much better solution. The good solution is do some kind of compensation with a reference, with a stretchable scale, some ideas like this. But a much better solution is actually don't measure the stretching, measure the resonance. Okay, and that's totally gravity independent. Matter of fact, there used to be one scale on the market which worked like that. And their ad said this scale is accurate even on the moon. I don't know if they still make it, but they made a big thing out of it that it's gravity corrected. Because the lab scales that you have today, they use strain gauges. So it's like springs. Okay, so there is an issue with gravity. When you go into the accurate lab scales which measure to milligrams in your labs, chemistry lab, these are all basically springs. They don't work like this inside. The old lab scales work like this. You put weights or sometimes automatically and balanced. But the new scales are all strain gauge based, so they are sensitive to gravity. Although you could easily put in a correction, put in a proof mass and correct it to gravity, but they don't. Okay? So one company said, let's do it this way. You put the weight on this platen, but the platen resonates. And the resonance can be very small amplitude. You barely notice it. You know, it can oscillate at 1 micron amplitude, right? But it's very easy to measure accurately a frequency. And we learn it later on in the course too, that anything you can convert to a frequency, you can measure much more accurately. Because, again, this will come up later in the course, it turns out that all the variables in the world you can measure to about 1 part in 1 million. So say you can measure voltage of 1 volt to 1 microvolt. You can measure 1 kilogram to 1 milligram. So almost you can measure 1 meter to 1 micron. So it's all 1 part per million. There seems to be a limit that everything you can measure only to 1 part in a million except time, where you can measure it to 1 part in like 100 billion or trillion. And it's actually a philosophical question. Why can you measure time so much more accurately than anything else, like 1,000,000 times more accurate? Just think of it. If you get like the time signal, like the satellite, some very accurate time signal, even a normal watch measures time to 1 part in a million. Cheapest watch, because the cheapest watch will be accurate to a minute a year, which is about 1 in a million. Okay, like any quartz watch, but you can get a time signal which is accurate to a microsecond, and this is generated from some atomic clocks. It's like same as the GPS system has. So if you can get a signal which is accurate to a microsecond, this is like 100 million millions, right? So strangely enough, if you can convert something to a frequency, you can measure it to a phenomenal accuracy, much higher than anything else. So because of that, when you think of sensors, if there is some sensor which lends itself to convert the measured quantity to frequency, you're way ahead. And this again, they took advantage of this idea. Okay, so I think you got the general message that you can have a simple sensor which could be affected by many things. To correct that, you can have a reference, and you can correct a lot of the errors, either by measuring the conditions or by comparing to a reference. Another way to get even more accurate is to measure it to known quantity under the same conditions and use a null sensor to just tell you when they're equal, okay? And these are the most sensitive systems. And that's about it. Now, there is another concept we should get into in a minute. Now, in measuring, let's talk for a moment about measuring electrical quantities. Let's say measuring resistance. So there is 2 ways to measure resistance. One is an ohm meter, like you have in your multimeter. And what is the other way of measuring resistance?
Power?
Pardon? No, resistance, electrical resistance. I want to know how many ohms this piece of wire have. So one method is an ohm meter, like you have in your labs. An ohm meter sends a current through it, measures the voltage. Doesn't matter how complicated it's inside, the principle is always the same. You send a current, measure the voltage, and you know the resistance. Okay? That's how an ohm meter works. But there is a much more accurate way to measure resistance. And that's how, if you want to measure resistance like to 6 significant digits or something, that's what you use. Yes?
Put a capacitor on it and you measure the charging time for the capacitor?
That wouldn't be more accurate. That's a very valid method, but it's not going to be more accurate than measuring the current and the voltage. Although you could convert it to time because you can make it oscillate, like an RC oscillator, but it still wouldn't be more accurate for reasons I wouldn't get into right now. But what is a historical way of measuring resistance? So when you have strain gauges, have you worked with strain gauges in the lab? So how are strain gauges connected to the computer? What is the configuration of strain gauges? This will give you a hint, yes? Wheatstone bridge. Okay. So how many people here know how a Wheatstone bridge works? So you should have thought, some people know. Good, so you should have thought of it. So Wheatstone bridge is a null sensor for resistance. It's the same thing as a scale, but for resistance. And the way it works is like this. The way it works is you take, typically it's drawn like this. You take 4 resistance. This is say plus V, that's a battery. Let's say this is ground, okay? And here you put a null sensor. A null sensor historically is just a meter, which you're just interested in 0. It's not calibrated, you just want it to show 0. It shows plus, it shows minus, and a pointer, it's a null sensor. Now, so let's say this is R1, this is R2, this is R3, and this is Rx. Rx is the unknown. You put in the unknown resistor, okay? So when will the meter show 0? The meter will show 0 when the voltage here equals the voltage here. So there's no voltage difference, the meter says 0, okay? When will the voltage here be equal to the voltage here? Each side is a voltage divider. So on this side, the voltage is just a regular voltage divider. In this side it will be Rx divided by R1 plus Rx times V. On this side it will be R3, the way I drew it, divided by R2 plus R3 times V. Okay? So when these two voltages are equal, then the bridge will be balanced. Okay, and you can write it out and you see right away. I mean, if I write it out, the V will cancel out. If I say Rx, just write it out, R1 plus Rx equals R3, R2 plus R3. The V on both sides cancel out, so it doesn't depend on the voltage, which is very nice, right? Because it's a null detector which doesn't depend at all on the voltage. Because when it's null at any voltage. It's a big advantage. So, okay, if I do the math, you'll see one term cancels out and it gets simpler. So here I get R1, R3 plus Rx, R3 equals Rx, R2 plus Rx, R3. Okay, so Rx, R3 cancels out. So basically what I get is Rx equals R1, R3 divided by R2. Okay, so that's a classic Wheatstone bridge formula. And when you use it in your labs, typically it's a strain gauge. You put a strain gauge here, and you put 3 resistors, and you balance the bridge. Any strain on the strain gauge which unbalance the bridge, and that's your signal voltage. Because the signal voltage will be proportional to the change in Rx. Clear? Because your signal voltage on this side will be proportional to change of Rx. Okay? So that's a Wheatstone bridge. And this is a very common, and that's actually a very common circuit in many sensors because it has beautiful properties. Okay, it's independent of the voltage, it's a null sensor, and its accuracy is only a function of the accuracy of these resistors. You can have a lousy power supply, a lousy meter, it doesn't matter. Because a meter is just used to detect null, doesn't have to be linear, doesn't have to be accurate, and the power supply doesn't matter because V cancels out. So that's a much better thing than an ohm meter. Because an ohm meter you have to send a very accurate current, which means if it's a normal current source, it depends on how many volts you have. You know, basically there's many sources of error. Yes?
So do you have to like manually adjust these R1, R2?
Yes, yes. So the way it's done in a real Wheatstone bridge, typically R2 or R3 is actually a set of resistors. The way this is done, instead of this, you have a set of resistors like every 1,000 ohms, every 10 ohms, every 1 ohm, and you select. So basically the way it works, you have a set of resistors, And here you select, this is each one is 1 ohm, so you select 1 to 10. Now here you have another one, each one is 10 ohm. And then you have another one, each one is 100 ohm. And you have like 6 dials, and you select, so that's why you get like a part in a million. And these resistors are made from material which doesn't change resistance with temperature and all the good things. But still, you only have to make an accurate resistor. You don't have to make an accurate meter. So it's a it still was invented 150 years ago, roughly. It's still the best instrument there is, and still it's a classic method to wire strain gauges, wire everything with very small changes. Okay? Why was it invented, by the way? Why did people 150 years ago really care about resistance to such accuracy? I'll give you a hint. It has to do with the predecessor to your smartphone. So think what came before the smartphone, before the telephone. Telegraph. And why was it so important to know the resistance in telegraph days? Okay, so I'll tell you the story. In the old days, when 150 years ago, there were no plastics. So if you wanted to bury telegraph cables in the ground, it was hard to insulate them. The only thing you had is 2 things: pitch, tar or pitch, and you also had a material called guttaperca, which is a precursor to rubber. Rubber is made from a rubber tree, but before Goodyear figured out how to make rubber out of the resin of rubber trees, they just used the resin itself. Caoutchouc resin was called guttaperca. Anyway, they didn't have insulators. The only insulators we had were not so good. So when they buried cables, when they buried telegraph cables, okay, there were many shorts. So there was 2 stations, and they buried the telegraph cable, and one day there was a short. One day the signals didn't go through, and they measured here with an ohm meter, and they saw there is a short. Now, if this distance is 100 kilometers, and there were telegraph lines which are thousands of kilometers, but even 100 kilometers, if you have an ohm meter which is accurate to 1%, and you measure the resistance from this side and the resistance from this side, you can estimate where the short is within 1%, right? Because the resistance is proportional to the length of the cable. So if this side measured 56 ohm and this measured 44 ohm, you knew that it's roughly 56 kilometers away. But if you used an ohm meter, the accuracy was 1 kilometer, 1%. Even today, the best ohm meters are about 1%. So you had to dig up a whole kilometer to find the short. But to dig up a whole kilometer in the mud, that's tedious. But if you had a Wheatstone bridge, it gave you the accuracy to within a meter. So it's much better to measure it with a Wheatstone bridge and only have to dig up 1 meter. Okay? So that's the history of the Wheatstone bridge, why it was invented, why it was so important, and why they wanted to have so many digits of accuracy. Because imagine if you lay a transatlantic cable, which is 3,000–4,000 kilometers, or if you lay even cables, which they were already at that time, there were telegraph cables laid across the US, okay, just across Canada, across the US, 3,000 kilometers, 1%, if there's a short, means digging up 30 kilometers. Sounds bad, but with the Wheatstone bridge, it will tell you within a meter where the short is. Okay? Good. But this Wheatstone bridge is a very good illustration of the concept of a null sensor. So the balance is a null sensor, and this is a null sensor, and many good sensors are null sensors. Good. Okay. By the way, you know, everybody draws a balance like this. So when people draw a balance, they draw a knife edge, and a beam, and 2 weights. Okay? But for some reason nobody stops and thinks, if a balance was really like this, why would it balance? Because you have an arm R and say in a weight W, so the moment is W times R times G. On this side, you have an arm R, W, the moment is WRG. But if the balance was tilted, you will get the same. If the balance was tilted, you'll get an effective arm, which is shorter. Okay? So the effective arm will be R cosine theta. But here, you also get the same shortening. So both effective arms will be R cosine theta. This is W. But it's still the same moment. Both sides you get W R cosine theta times G. So why would the balance balance? Okay? So, since you're all mechanical engineers in some part of your career, so think about it. I wouldn't tell you the answer, but it's surprising that I'll give you a hint. That's not how a balance works. Most people don't realize it. Okay? There's nothing to do with this course, just to keep you awake. So think about it. How does a balance actually work? Okay. So we finished with this, and now these are all historical old sensors. Now let's talk a little bit about more modern sensors. And again, I'm just picking examples of sensors to illustrate these principles. It doesn't really, the sensors themselves don't really matter. What matters is to understand these principles. So let's talk about modern sensors. So the most common sensors are sensors to measure displacement. And the reason why these are the most common sensors is that if you know displacement, you can, from displacement, derive other things. For example, if you want to know acceleration, you put a mass on a spring. When you accelerate, the mass deflects the spring. If you measure the displacement, you know the acceleration, right? If you had a cantilever with a mass, and you accelerate it, the mass will bend, okay? And if you measure the displacement, okay, and you know that the force is ma, and you know that the force is kx on a spring, so A is kx over m. So if you measured x, you could know acceleration. Okay? Another example, if you can measure displacement, you can measure pressure. You have a pressure vessel with a diaphragm like this. If you put in pressure, this will bulge out. If you have a sensor here which can measure x, by measuring x, you know the pressure P. Okay? So the reason why we are concentrating on displacement sensors, because there is a whole range of physical variables which can be translated to displacement. Like we talked before about mass on a spring can be translated to displacement. Acceleration is naturally translated to displacement. Pressure is, many other things are. Okay? So I'll give you many examples of displacement sensors because these are the most common sensors. So let's start talking about electrical sensors. And again, I'll show you two displacement sensors just as an introduction to some concept. So I have a transformer here, and the first displacement sensor is just an inductor, or what's called a solenoid, a hollow coil. The technical term for a hollow coil like this is solenoid. And when I put a light bulb in series, so when I have a coil like this, and I put a light bulb in series, and I run it from AC, because of course I have to run it from AC, not from DC, because a coil doesn't do anything in DC. Okay. Now when I put a slug into the coil, I have a piece of, say, steel, and I move it next to the coil or inside the coil, what will happen to the intensity of the light? Change. Why will it change? Pardon? not the resistance, but you're getting closer. What is changing? If I have a coil and I put a piece of steel and I move the steel, what am I changing? That's better. Okay. So I can build a displacement sensor by taking a coil and sending an AC current through it. So let's set for AC, putting up some current. Okay, so right now there's a coil and a light bulb. If I put in the piece of iron, will the lamp go brighter or dimmer? Okay, what happens to the inductance of a coil if I put in iron inside? Does it go up or down? Up. Most of you say up. Okay, we are a democratic society, so let's say it goes up. Okay, now, if the inductance goes up, what will happen to the current? Will it go up or down? Say it was resistance, not inductance. If the resistance goes up and is connected with a light bulb to a voltage source, will the current go up or down? So the consensus is down. So inductance is like resistance. If the inductance goes up, it's harder for the current to go through, right? So current will go down. Agree? Okay, so when I put it in, current will go down. But now I actually have a distance sensor. As I start pulling it out, current will go up and up and up, and it's not completely linear, but has a nice range, nice usable range, from maximum current to minimum current. It's not bad, actually, as a sensor. Okay? Now, what are the disadvantages of this sensor? Because this looks like a very simple sensor. You just have a coil and a resistor. The light bulb represents a resistor, measures the voltage of the resistor, and you can measure the position of the piece of steel in the coil. Okay, so it sounds like a simple, good sensor, high-level signal. You don't need amplifiers. It's good too. So, can somebody think of the disadvantages of this sensor?
You need a good sensor for measuring the intensity of the light.
No, but I said something else. The light is just to show it to you. But I can replace the light with a resistor, see, because the light is just for the demo. But in real life, the sensor looks like this. You have an AC source, which could be the power line, because I can do it on the line frequency. Now, I have this inductor here, which I move in and out a piece of steel, and then I put a resistor here, like the light, and the output is this. The output is the voltage of the resistor. So now I have a very cheap sensor, doesn't need a power supply even, because I plug it straight to the light, doesn't need an amplifier. Because this can be, I just showed you the light, can have a very big output. It's not completely linear, but you can make it quite linear, because the more iron is in the coil, the higher the inductance, so you can actually make it quite linear. As you saw here when I moved it, kind of first look, it looked pretty linear. So why aren't, and also it's non-contact, because this piece of steel doesn't have to contact the coil. So if this has to move fast, it doesn't wear, it doesn't touch the coil. So this seems like a perfect sensor. So why aren't all distant sensors working like this? Yes?
The iron core changes properties as time passes, so its magnetic properties changes.
Okay, so now we start thinking, remember, a good sensor measures what we want, but nothing else. But this actually, if the voltage here changes, the output changes. If the iron core changes properties, whatever. But there's other more nasty factors. What happens if the temperature changes, if the coil heats up? Because you used it a lot. What happens? Resistance changes, okay? A good number to keep in mind is copper. Most coils are made of copper. Copper changes resistance 1% for every 2 degrees Celsius. Okay? Again, if you want to be in technology, there is a long list of things you always have to keep in mind that you don't have to look up. And one of the things is what I showed you before with how to approximate error. The other thing you always have to keep in your mind is some properties of key materials like copper, steel, aluminum, stainless. Otherwise you can't think fast. So copper changes 1% every 2 degrees. So that's very bad because this can heat up 20 degrees, it's 10% error, right? So the main reason why this sensor is not used much, it is used but not much, is the temperature effect. The iron heats up and changes a bit magnetic properties. The copper heats up, changes resistance, because when I draw it like this, you don't see the error, but there's actually a hidden resistor here. And that hidden resistor is the resistance of the coil. But this changes 1% per 2 degrees C. So that hidden resistor throws in a big error. Okay? So now I'll show you another sensor, which is also coil, but it's built differently, and then we'll discuss its merits. So the other sensor uses 3 coils. It has one coil in the middle. It has one coil in the middle connected to the same AC source, let's say the power line, and has 2 coils here. And these 2 coils are connected to cancel each other. So in other words, if you induce a voltage, as you know, 2 coils together form a transformer. Right? If you put voltage on one, a voltage will appear on the other because there's magnetic field which couples them. Okay? You know that. Okay. So let's say that if I have a field here, and this is like minus plus momentarily, I want to connect it that it's opposite. I want to connect it, I want to wire the coils that it will be like this, so the coils cancel out. So so this is the output. Okay, and in the test I put a light bulb here too. Okay, now when I put a magnetic slug in the middle, this is the same steel slug, this voltage will equal this voltage, they'll cancel out, I'll get no signal. But as I move to one side, so I'll get big coupling to this side and low coupling to this side, so the voltages will no longer balance out. Is that clear? Okay, let me show you how this works. Now this thing, turns out, is the most popular distance sensor there is actually in the world. And does somebody know what it's called? LVDT. Okay, so you heard of that. That's good. Okay, so LVDT stands for linear variable differential transformer. Okay, so this it is. There is a coil. Actually, this is wired opposite. The excitation here is on the outside coil, the pickup is on the inside coil, but it doesn't matter. Because that is a linear system, I can reverse it, I can drive it opposite. So as you see, the input, the AC comes in at these coils, and the middle coil is such that in the middle there is no field, because the coils are wired to have opposing fields. So there's a light bulb here, it doesn't turn on. Now, if I put in a piece of steel and I hold it asymmetrically, the light bulb will turn on. Okay? So if the steel is exactly in the middle, okay, exactly middle meaning like this, then again, this field and this field will be exactly the same. In the middle, the 2 fields will cancel out, I'll get nothing. So if I line it up, this is roughly the middle, and I hold it, the green mark here is where it's in the middle. So when I put it up to the green mark, I get nothing. You see the green mark in the middle. But if I pull it to one side, the signal is pretty linear. And in reality, if you measure it, it's actually very linear. And if I push it to the other side, I get the same. I get a very linear behavior up to the point where the steel goes out, and then I get nothing again. Because if the steel goes out completely, it's symmetric again. Okay? So as long as it's symmetric, with or without steel, I get 0. Okay? But if it's asymmetric, the steel couples 2 coils, but not the third, the field from this side is much stronger than from this side, so the middle coil, which measures the difference. Okay, so I hope it doesn't confuse you that, oops, it gets hot. I hope it didn't confuse you that I drew it. I drove it too hard, it got too hot. So I hope I didn't confuse you by the fact that I drew it that the excitation is in the middle, but actually the demo, the excitation was at the end. So what you saw in the demo is a little bit different. It had the 2 coils wired to cancel each other. So the magnetic field was canceling each other, and the sense coil was in the middle with a light bulb. So as long as there is nothing, no slug, these two fields cancel, there's no field in the middle. If I put the slug, I got strong coupling between these two, and this one didn't do much. So I got a voltage. If I move the slug to the other side, these two coupled. Okay? And this whole thing is called an LVDT. Okay, so what makes this better than the original sensor, which looked so much simpler? Both run on AC without a power supply. Both have a big signal. You don't need amplifiers. They seem both pretty good. So why is this the most popular sensor, and this is only used when low cost is like an absolute must? Yes, please.
Do you have a reference again? So the temperature, 1 hectare?
Okay, so I don't really have a reference, but you are right, because there is no reference here, but there is cancellation of effects, because if the thing gets hot, this gets hot, this gets hot, this gets hot, but the operation stays the same, okay? Because first of all, I'm measuring the voltage, so the series resistance doesn't matter, okay? But the main thing is that what I'm measuring is a deviation from symmetry. So if there is a change in temperature, inductance, and anything, it affects both sides the same. So I'm only left sensitive to one thing, to this voltage. Because if this voltage changes, I'll still get an error because the signal here is proportional to this voltage. Same as here. The signal is proportional to the voltage. But here it's also affected by the change in resistance, by many things. Here it's only affected by the voltage and by the placement of the piece of steel. Okay? But there's a lot more subtle points which are not so clear here. And I'll start going through the subtle points, and we'll continue next week. But I'll show you some of the subtle points. Okay? So first of all, I said that this really is only sensitive to the symmetry. So in a way, it's a bit like a Wheatstone bridge. In a way, it's like a null sensor. Where in the middle, it says null. It measures deviation from null, except here I'm using it not just to sense the null, but over a full linear range. But I could use it just to sense the null position with great accuracy. And then I don't depend at all. If I want to align two things, and I just want to sense one position, to sense the middle position, it doesn't depend on anything. I can put a meter here, just make sure the meter says 0. Then it's exactly in the middle. Okay? But it turns out there is a lot of other subtleties where this is better. Let's say over time things age, coil changes, magnetic things change. It will affect this much less because the three coils are basically the same. And what I'm really measuring is the symmetry of the situation. So if this coil will get more resistance, this coil will get more resistance, the calibration wouldn't change. So if I can normalize it, normalize means if I can take out the amplitude of the equation, then everything will be stable even if there's lots of changes. And what I mean is here I can keep the voltage constant, but I cannot take the other variables out of the equation, like the increased resistance, the change in magnetic properties. But here, let's say I call this coil, I call this voltage VA, and I call this voltage VB. So the output is VA minus VB. And it depends on this voltage and so on. But if I divide it by VA plus VB, so not only I take the difference, I take the sum in a different circuit and I divide. It cancels out all other variations, because if the power supply goes up, each one of those will go up by a factor k. Okay? So now if the power supply goes up by a factor k, it will be kVA minus kVB, k, so all the k's will cancel out. Okay? So basically, if the whole thing changes by a factor k, I'm going to get kVA minus kVB, kVA plus VB, and the k's will cancel out. It will go back to this. Is that clear? So that's called normalizing. This idea is called normalizing, to do the difference divided by the sum. Now I can't do it here because I don't have an A and B. I only have A. So I don't know what to do. I don't know how to normalize it. Okay? I mean, I could measure this voltage and do V divided by this voltage, which gives me some normalizing, but if there are other changes inside, I don't know how to normalize it. But here, because I have a differential sensor, I can normalize it, and that's a huge advantage. And this type of sensor is called differential, and most good sensors are designed to have this property. So we'll continue next week to dwell on this property, and if you are really bored, think of the question of the scale. How does the scale really work? See you next week.